You may not have noticed, depending on when you left, that Andres put the Wi-Fi info on the blackboard. Can you see it? Does everybody see it? Can I roll this out? Mm-hmm. Okay. So there's two screens. By this point, are your two eyes each on different screens and things getting blurry with all the philosophy? We're going to start getting a little more concrete, gradually working our way up to more practical things. Does everybody have this now? I suppose there might be some creative way to do 3D with these two screens. I don't know. With special glasses, but it's beyond my technological capability. Let me pick up with this remark by Jeffries to say just a few brief words about how do you interpret these Bayesian probabilities. I said it's a strength of an argument on some scale from 0 to 1. So how do you interpret that? And I'm going to kind of pick up on this remark by Jeffries. Essentially, the notion can only be described by references to instances where it is used. So another way to say that is that it's an abstraction. Probability is an abstraction, like most of the math that we use in physics. The value of an abstraction is that it tells you something that's shared by many instances of that abstraction. So mass, right? A ball can have the same mass as a piece of rock as a volume of gas, but the number mass refers to something that's the same between them. That idea of mass is something that's kind of pretty abstract. If you think of it, the notion that there is something the same about a volume of mass or a ball, a tree or something, things that occupy different volumes or something that still have the same property. That's a kind of pretty abstract idea. Probability is an abstraction in the same way, that we can try to kind of calibrate how we interpret it by connecting it to connecting probabilities of things we're familiar with probabilities of things that we're not. So what am I getting at there? So let me make an analogy to another scalar that appears in physics, and the analogy is actually more than superficial, and that'll be between temperature and probability. I won't go into any depth in it, but there actually, as you know from statistical mechanics, there are deep connections between temperature and probability. I just want to make a fairly superficial connection. So there's some temperature quantity, T, that we can assign numbers to. And what does it mean to say something has the temperature of 273 Kelvin? Well, we know ice at the melting point has temperature 273 Kelvin. So if I told you this desk had a temperature of 273 Kelvin, you'd know something about what it would feel like for me to touch it, because you know what it feels like to touch ice near its melting point. Or the number 373 Kelvin, we calibrate our understanding of what that means in terms of temperature, because we know boiling water just at the boiling point has that temperature. So similarly with probability, we can take probabilities for things that we have an intuitive sense of the degree of uncertainty and map, and the probability scale then lets us map that intuition to other problems where that same value arises. So we have pretty strong intuition about what certainty and falsity mean. So there's no problem understanding what probabilities of 0 and 1 mean. But say in some statistical analysis of some complicated data, you found a probability near the value 1 over 36. Well, you probably know from playing games of chance as a child, you probably have some sense of how likely it is in a single roll of a pair of dice to get snake's eyes, 2 ones, right? It's that same level of plausibility that you would map to your scientific problem that has that same value of probability. Or you have some notion that if you fairly flip a coin 10 times, how likely it is to get all heads. Right? That's a probability of about 1 in 1,000. So if you, in the course of some probability, Bayesian probability calculation, you assign a probability of 1 part in 1,000 to a hypothesis, you then have some idea of what that corresponds to from your experience of this other problem, flipping coins, and what its probabilities were. So that's, in Bayesian probability theory, that's the way you kind of intuitively calibrate what is meant by a certain value of probability. By being an abstraction, it's what lets you map equivalent kind of states of uncertainty between problems where you have some idea of that from experience to problems where the algebra led you there, not experience, but now you can map your experience over. Just one other slide on interpretation. The Bayesian and frequentist understanding of probability means that you should think very differently about probability density functions, the things that we end up using a lot, probabilities over real numbers. So in a Bayesian probability density function for some quantity x, say the mass of an exoplanet, say I do some calculation that gives me a probability density, maybe a prior or a posterior probability density for the mass of an exoplanet. So that's some density function, p as some function of x, a curve as a function of x. The way to think about that in from the Bayesian point of view is that that curve describes to you how the probability is distributed over the possible values of x. The planet itself has one unknown true mass value. There's one unknown true value. It's the probability, your probability for what the true value might be, that's distributed over the full range of x. It's kind of like a classical mass distribution where there's, space, three-dimensional space, and rho of x talks about how this stuff mass is spread out through space. In the frequentist point of view, probabilities are always kind of long-run rates or proportions or frequencies that tell you about how some outcome varies from trial to trial. A frequentist probability can always be thought of as some kind of histogram, where the thing you're talking about, the probability of x, takes on different values in an ensemble, in a sequence of experiments, and the curve is just the histogram of those values. In a frequentist probability density, you think of the x values as being distributed. The probability density tells you that in many repeated trials that the x will take on different values, and the p of x curve is just the histogram of what those values are. Yeah, that's pretty much all I want to say. So frequentist PDFs are basically histograms. It's the x that takes on different values. Bayesian probability density functions are like mass density functions. The x has one unknown true value, but you're spreading your probability. It's the probability that's being distributed, not the value of x. And that's reflected actually also somewhat sloppily in the way that we would read this notation that I gave you before. X, twiddle. You might remember I showed you this kind of statistician's notation for that corresponding to p of x equal to a Gaussian. So, strictly the way a Bayesian would read this is the probability for x is distributed like a Gaussian. And the way a frequentist reads this, and it's just by default that's the way most people just say it, is that x is distributed like a Gaussian. Do you get that? It's a different meaning to what the way you're interpreting that p of x. All right. So now that you have those three rules of probability theory, let's derive some theorems. Like any mathematical theory that has axioms, you use the axioms to derive interesting theorems. I'm going to show you three theorems, and basically those three theorems are equivalent to the axioms. Once you know these three theorems, you can, for most practical purposes, you can forget about the and or not formulas. These formulas will be the ones that you'll find yourself using over and over again. One of them will be Bayes' theorem or Bayes' rule, where this approach gets its name. But I'm going to argue in the rest of my lectures that actually the most important theorem probably isn't Bayes' theorem. It's probably another one that we'll talk about. And so maybe Bayesian inference is misnamed in that respect, or has had the emphasis in the wrong place. But the point is that probability theory isn't, the Bayesian approach to Bayesian inference isn't just using Bayes' theorem. It's using all of probability theory, all the theorems that can be derived from it in a particular way to reason from data to hypotheses. So the Bayesian recipe is that when we're looking at, we're doing data analysis, we're going to try to calculate the probabilities for some hypotheses about nature, conditioning on different types of information, including most notably data, which I'm going to denote generically by D, using the rules of probability theory. So let me just restate those three axioms we kind of motivated before, but now kind of suggestively plugging in H for hypotheses about nature and D for data. And I is a common symbol that's used for just all the other background information in the problem, the other premises, like models, things, modeling assumptions, things like that. I for information. I sometimes use C for context. I actually prefer that. So here's that OR rule. I just wrote it out. It's the same one you saw before, but with different symbols. The probability that either hypothesis 1 or hypothesis 2 follow from our premises is just the sum of their probabilities minus a double counting term. The probability that a particular hypothesis and the data, the particular observed values of the data, follow from our various premises, including models, can be written two different ways, factored two different ways. P of H times P of D given H, all of them given I as well. Or I can reverse D and H. And we'll see this again in a slide or two. And then the not rule, just the probability that hypothesis 1, the denial of that follows from our premises is just 1 minus the probability that the hypothesis itself followed. All right, so the first of our three important theorems is Bayes' theorem. So let's look at that joint probability that I just wrote out for you. P of H and D given I, P of H given I, P of D given H and I, or I can reverse D and H. So I already told you that the Bayesian recipe is to seek things that look like this. The probability for hypotheses of interest to us given some premises that include the data. So this thing is called the posterior probability for the hypothesis. Posterior, not meaning in the sense, not referring to time necessarily, meaning after consideration of the data. So let's solve for this. Let's set these two right-hand sides equal to each other and solve for this. So P of H is this divided by this. And I just wrote that out here. Here's the P of H, P of D given H divided by P of D. This theorem, just in terms of generic symbols, it holds for any propositions, but in particular when you have hypotheses here and data on the right-hand side, then the different factors have special names. I already told you the term on the left is called the posterior probability. This thing is called the prior probability, meaning prior to consideration of the data. Of course, you might have started your calculation after you have the data, but this is what the probability is before you consider the data. And then this thing here is a probability for the data, but it's clearly telling you something about the different hypotheses and how one should be preferred to another. So it's given a different name than probability when it's looked at as a function of the hypotheses. It's the likelihood for the hypothesis. I'll say more about that in a second. And then this thing in the bottom, it doesn't depend on the H's, so it must play the role of a normalization constant. We'll say more about that too in a minute. It also has a name the prior predictive probability. It's that without referring to which particular hypothesis may be true, it's what's the probability that you predict for seeing the particular observed data that you have. Okay, theorem number 2, and this is the one I would argue is the most important theorem. Theorem 1, I'm going to argue throughout these lectures, is important only because it lets you apply theorem 2. So theorem 2 is the law of total probability. So let's suppose we have some exclusive exhaustive set of propositions or hypotheses. In other words, the premises assert that one and only one of them must be true. Now, for reasons that will be motivated in a minute, let's look at this particular sum of probabilities. I'll take the joint probability for A and one of these auxiliary hypotheses, and I'm going to sum it over that second slot, over B. Now, this is a joint probability, so I can write it two different ways. I can write it as P of A, P of B given A, or I can write it as P of B, P of A given B. So I've written it both ways here. Now, let's look at this first one. P of A doesn't depend on I, so looking purely mathematically, I can pull that out of the sum. So then I have a sum of P of B's. But I've told you that that's an exhaustive set. One of them must be true, and only one of them. So the sum of those probabilities is 1. So that means this sum here is just P of A, the thing that I took out of the sum. Which means this thing here is just P of A. If I take a joint probability where one of the slots refers to exclusive exhaustive possibilities, and I sum over that slot, what's left is just the probability of the thing that remains. And then the second line just tells me that another way I can write this P of A is as a sum of P of A given B weighted by P of B's. So why am I making such a big deal out of this? So there's two ways this will appear over and over again in calculations. One is that sometimes we'll seek a certain probability. We'll have some hypotheses of interest. We'll call them A here. And we need to calculate this, but it won't be obvious how to calculate this directly from our premises. If only we can find a set of auxiliary hypotheses, then this law, this particular, actually setting this equal to this, lets us introduce these B's as a kind of basis for expanding this probability in terms of other probabilities we might know already. This is sometimes called extending the conversation. I like to think of this as the probability theory version of just expanding a function in an orthonormal basis. It's the exact same idea. Instead of orthonormality, we have exclusive exhaustive property. So this says P of A, if I can introduce a B so that if I knew B, then I would know P of A. Then all I have to do is take those probabilities, weight them by the P of B, and that gets me the desired probability. So it's like an orthonormal expansion. So that's one use of the law of total probability. The second use is something called marginalization, where if my calculation gives me a bunch of joint probabilities, but I'm only interested for a particular question in the probability of one of those things, I just have to sum over the other to get it. That's called marginalization because you imagine listing these probabilities in a table where, values of A are along the columns and values of B are along the rows, and then in the margins you list the sums across the rows and the columns. That's why this law has this funny name, marginalization. It corresponds to those marginal totals in a table. Okay, so that's the law of total probability. Let's give it one slightly abstract use right away. So take A to be the statement that the data are what we observed, and the B's to be some set of hypotheses that we're considering as descriptions of the situation in our experiment. Then suppose I want to calculate this thing which appeared in the denominator of Bayes' theorem, this prior predictive probability. Well, the law of total probability says I can just insert H and sum over it. So P of D given H times P of H. But this thing here is just what was on the top of Bayes' theorem. So the law of total probability shows you what we argued was true earlier, just that the bottom of Bayes' theorem has to be the normalization constant, the sum of the top. So we just argued that must be the case because it didn't depend on H when we derived Bayes' theorem. But here, with the law of total probability, we can show it explicitly. So this thing here is the likelihood for H. And so this sum is a weighted sum of those likelihoods. So the prior predictive probability has another name. It's sometimes called the average likelihood, or most often the marginal likelihood, because it's this kind of weighted averaging over the likelihood function. And then the third theorem is a pretty trivial theorem. It just comes from that not rule and the sum rule together. I'll leave the proof to you. It's pretty straightforward, that if you have exclusive and exhaustive H's, the sums of their probabilities have to be 1. So those are 3 theorems in probability theory from those 3 and or not axioms. And if you know those 3 theorems and you understand them, you basically know all the probability theory you need to know for most calculation purposes. Well, just one word about this. So all these theorems and all the axioms, they tell you how to calculate some interesting probabilities in terms of other probabilities, right? If ever we want to get a number out of these calculations, an actual probability for something of interest, then we have to insert a number somewhere. All these rules only relate probabilities to other probabilities. They don't tell you how to actually assign a number to a probability theory. So probability theory, understood in a limited way to just refer to these rules, is incomplete for our use. It tells us how to relate probabilities, but it doesn't tell us how to assign some probabilities to begin with. Right? So direct probabilities, that's a term that we use for the particular probabilities that will, based on some models, other aspects of probability theory, that we'll actually be able to assign numerical values to by some kind of mathematical argument. And then probability theory will then let us calculate other desired probabilities from those direct probabilities. So a problem is only well posed if we have all the direct probabilities that we need. And sometimes, all the elements of our model, physical reasoning, symmetries, things like that will give us all the direct probabilities we need. Other times we're going to have to do something like Euclid did with his 5th postulate. We're just going to have to say, okay, I have almost everything I need, but I have to make some assumption. I'm not totally comfortable with it, but here it is. Here's the assumption I'm making. And maybe you want to explore the sensitivity of that assumption. But sometimes we have to make, assumptions, just as with deductive logic here, sometimes we have to make slightly uncomfortable assumptions to make a problem well posed. Okay. Now, let's get a start on inference with parametric models. We'll finish this after the coffee break, but we're going to take this now only slightly more concrete theory and make it a little more concrete by talking specifically about parametric models, kind of the bread and butter of kind of day-to-day data analysis. I'm not going to talk about something called non-parametric models in these lectures. I don't know if anybody is. Brendan, are you talking about any non-parametric models? Maybe Jean-Luc will, I think, a little bit. But we can talk about that offline. But let's talk about parametric models. So inference with parametric models. Well, what am I talking about with this idea of a parametric model? So our scenario here is that we have some set of models, and I'm going to label them by I equals 1 to n. Each of them has some parameters, some sets of variables in the model that each imply a sampling distribution. That is a probability for possible values of the data that's fully specified if I've identified the model and the values of its parameters. Like in that Gaussian example before, the model was that I'm assuming Gaussian additive noise. The parameter, which I'm calling theta here, was mu. So this is what I mean by a parametric model, that if I tell you my model choice and fully specify the values of all of its parameters, then I can tell you the probability for any possible data set. The theta dependence of this thing, if I plug in only specifically the observed data, that's what's called the likelihood function. So plug in the observed data. So this is the sampling distribution probability for any hypothetical data set. This is the likelihood function, the probability for the observed data set, focusing our attention on how that varies with the parameters. Now there are two things that we might be uncertain about in this. We might be uncertain about what model to choose, and given a particular choice of model, we might be uncertain about its parameters. And so we need to attack both types of uncertainty. Now, for the rest of these lectures, we're only going to be looking at the observed data. We're not going to be doing frequentist calculations where you'd have to look at sums of this over hypothetical data. We're doing Bayesian calculations. So henceforth, whenever I talk about data, I'm always talking about the observed data. And I'm going to drop this cumbersome subscript, but I always mean observed data. All right, so I'd like to distinguish three classes of problems, and then within each one there are different kind of sub-problems. There's single model inference, where among our premises, among the things to the right of the bar, is going to be the choice of a single parametric model. In that general scenario I just described, we're assigning a particular value to I, that index I. If I have more than one model, I'm going to focus for single model inference on one of them. And so two of the types of problems that arise in single model inference are parameter estimation. What can we say about the parameters of that model, or some interesting function of the parameters? Like, what can I say about, the period and the velocity amplitude in a radial velocity model for some exoplanet spectral data? Or what can I say about the planet's mass, which is a nonlinear function of those things in an unknown inclination angle? So parameter estimation. Another problem is prediction. Given the observed data that I have, what can we say about possible values of future data? That might be important for planning a future experiment. You want to know what future data might look like, given what you know about what you've learned from past data. There's also multi-model inference, where my premise is that one of a set of competing models is going to be, I'll assume one of a competing set is an accurate description of the data. So among the problems that might arise there are model comparison or model choice. So which model is the best description of the data? What can I say about this integer valued parameter, if you will, I? Another type of question that arises that's worth spending time on, but we won't have time to spend much time to spend on it, is model averaging. That is, it's often the case that among a competing set of models, there are some interesting parameters that are common to all of the models, but each model has its own set of extra parameters. So this arises when particularly talking about systematic error. So suppose I'm looking at a time series, some variable star or whatever. Gamma ray bursts is something that I work on, gamma ray burst time series. So I'm interested in the inferences about the light curve of the gamma ray burst, but there's a background rate that's varying in time. How does the background vary? Is it constant? Maybe there's linearly varying background. Maybe it's some polynomial is required to estimate the background. I have data before and after the burst that I'll use to try to constrain that. But I don't know a priori which of those models might be true. So I could imagine having several models for the data. All of them have some light curve parameters, phi, but the different competing models have different background parameters, a constant background rate or an intercept and a slope or other terms. So I might want to say, well, what do I know about the gamma ray burst light curve? Not committing to one of the background models, but letting the data establish the constraints for those models. And maybe the data will strongly favor one background model over another, but maybe it won't, and I want to take into account the uncertainty in those models. So that's a case where you do this thing called model averaging, where you want to take into account the fact that you have these competing models with different extra parameters. What do they all say about the common parameters, just the light curve? Or there's prediction, where what can we say about future data, accounting for the fact that we don't know what model is true. So exoplanets. I have some data on a planetary system. I don't know for sure with the data that I have whether there's a planet there or not, but I need to plan future observations. What can I say about what the future data might look like as a function of time, given my uncertainty in whether there's a planet there or not? There's actually a theory that I've been involved in working out on how to optimally schedule your observations, taking into account, your current uncertainties, and you have to do kind of averaging over models as well as parameters to do that. And then a final class of problems is model checking, where you could think of this as the premise being either a particular model of interest is true or something else is true. In other words, I want to kind of address the question, is this model of interest, the one I'm focusing on, is it adequate? Is lambda CDM good? Without committing to a particular alternative. This is actually hard to phrase in a Bayesian point of view. It's something that can be phrased in a frequentist point of view, but in many different ways. There's actually some powerful recent theorems in frequentist statistics that say that there can never be one single way to answer questions like this. But anyway, that's called model checking, and there are ways to attempt to formalize it involving non-parametric alternatives, and there are kind of frequentist ways to formalize it involving comparing predictions, and it's all worth talking about, but we have limited time, so we're not going to talk about that. But I just want you to be aware of that area. A good place to look about this for the Bayesian point of view, this is Andrew Gelman's book, Bayesian Data Analysis. Gelman, Rubin, and some other authors, they devote a lot of effort to Bayesian versions of model checking. All right, so let's talk about single model inference, the parameter estimation problem. So here our premises, our kind of context for reasoning is that there's a particular model we're going to focus on that has parameters theta. And our hypotheses are going to be statements about the parameters, like that a parameter, in this case a scalar parameter, lies in a certain interval, or that a parameter is non-zero, positive and non-zero. Now, the probability for any such statements about a real parameter can be found if we know the probability density function for that parameter. So, in particular, the probability that theta is in this infinitesimal interval, I can write as a function of theta times the size of the interval, and that thing is the probability density function. And I can get the probability for this just by integrating over this interval. I can get the probability for this just by integrating over every value bigger than 0. So I think you're all familiar with probability densities, but I just want to point out the reason they're interesting is because they let you get probabilities for kind of finite statements about parameter space. And I will leave for you to prove that Bayes' theorem, which we derived for probabilities, also holds for probability densities. Just be careful, and in Bayes' theorem, plug in probabilities. So if you knew the density, you have to include the d theta. You'll also have dd's, intervals for the data, if the data are real value, and you'll see that all those differentials cancel. And so Bayes' theorem holds for densities as well as probabilities. So here I've written it out. The posterior density is a prior density times the likelihood function divided by a normalization constant, just the integral of the thing on the top. For Bayesian inference, estimation is calculation of this density as a function of all values of theta. That's the answer to the parameter estimation problem, that entire distribution. But of course, to communicate it, you often want to summarize it in some low-dimensional way, and I just want to make sure you know the lingo for some common low-dimensional summaries. For a point estimate, some kind of best fit value in some sense, there's the mode, theta hat, which is the one that maximizes the density. There's the posterior mean. So you take theta weighted by its density and integrate it. That's the posterior mean. In general, these will differ. For a Gaussian, for example, they're the same. To communicate uncertainty, you would calculate a credible region with some probability content C. That's just some region, which I'm denoting by a big delta here, such that if I integrate the posterior over that region, the probability that theta is in that region is the number C. In general, there's all kinds of integrals like that you could calculate. The one that has density inside it higher than density outside, like that red region in that Gaussian that I drew before, that centered red region, that's called the highest posterior density region, or HPD region. Density is higher inside it than outside it. That also happens to be the smallest region with a given content. Of course, you can calculate posterior standard deviations just by squaring here and then subtracting the mean squared. Posterior variances, covariances, similar to things you already, variance and covariance and frequentist calculations. Now, an important new ingredient in Bayesian inference is the marginal distribution. If the problem has parameters of interest phi, but then additional parameters like a background parameter, which I'm denoting eta for extra, then from the law of total probability, the probability density for the parameters of interest is just the probability density for all of the parameters integrated over the nuisance parameters. Now, this is an incredibly important, one of the most important things that Bayesian inference gives you, and it's coming from the law of total probability here, is marginal distributions. So let's think a little bit more about what they mean and what that calculation is doing, that integration. So to model most data, we need extra parameters. And so as a example, think about data that we have from measuring a total rate, that's signal plus background. We have additional data about the background. And so we want to know, what does the data tell us about the signal? So I'm just plugging in these symbols S and B where I had phi and eta before. The marginal posterior density for the signal is the joint posterior density for signal and background integrated over background. So that's just the law of total probability. But now let's start kind of looking at this integral and seeing what it means. So this is a prior times a likelihood. So I'm going to write the prior as P of S and then P of B given S, given only the model. And then there's a likelihood function that's a function of both the signal strength and the background strength. So I've pulled the P of S out of the integral because the integral's over B. So this is the prior for the signal times this integral, which I'm calling the marginal likelihood function for the signal, L sub m of S. And it's just defined to be this integral. So let's think about what this integral is doing. That's the next slide. So the probability for the prior probability for the background given the signal, usually the background has nothing to do with the signal, so that'll just be a prior for the background, times the likelihood for signal and background integrated over background. What on earth is that integral doing? All right. So let's suppose that the prior is broad compared to the likelihood, and I'm going to show you a plot on the next slide trying to make this concrete. So in other words, there's this likelihood function we're assuming the data tell us a lot about the parameters, so that the likelihood function is some concentrated thing. The prior is something expressing ignorance, what little we know without the data, so that's something that's roughly constant. So that means for a fixed value of S, we can accurately estimate the B by taking its by maximizing the likelihood function. I'm going to call that b hat of s. So for a particular value of s, I find the value of b that maximizes this. That's this b hat of s. And that the width in the b direction will be delta b of s. So let me see. Let me first show you. So here's that joint likelihood function. It's tilted in the negative direction because we imagine there's a constraint on the total rate. So that means if the signal is high, then the background must be low, or if the signal is low, the background must be high. And what I'm saying here is that for any particular value of the signal, I'm going to pick out what, for that value of the signal, what's the best fit value of b, that's b hat of s, would be this point here. And then what is the uncertainty in the b direction at that value of s? So that's the width of this two-dimensional thing, but just in the b direction. And here I've drawn it for a Gaussian case where it so happens that every cross-section has the same shape. They have different heights, but if I make them all the same height, they all have exactly the same shape in the Gaussian case. So at every value of s, there's a different value of b hat. At every value of b hat, there's a different, potentially different, but in this case, the same width of that likelihood curve. Let's go back. So now I'm going to approximate this integral. I'm saying the prior is roughly constant, so I'll just evaluate it at b hat and take it out of the integral. And then I'll integrate the likelihood function by just taking its peak value times its width. Area under the curve, peak times width. So this marginal likelihood function is just the prior at the best fit value of the background times the maximum likelihood times the width of the likelihood function in the background dimension. Now this thing here has a name in frequentist statistics. It's called the profile likelihood. It's sometimes used as a tool for getting rid of nuisance parameters, but it's known not to be a good tool in general. It's known to work well for Gaussians, but not to work well in general. What's interesting here is that a Bayesian calculation is telling you, at least approximately speaking, that you should indeed calculate the profile likelihood. You should find the best fit value at a given s of the background, but you should then weight it by the background uncertainty. That's kind of the new ingredient that Bayesian inference is offering here, this kind of weighting by the volume in the nuisance parameter space. So what it's saying in this case here, because these cross sections have exactly the same shape, it's just weighting by a constant, and it's basically giving you a Bayesian explanation for why profile likelihood works well for things that look like Gaussians like this, even correlated Gaussians. Is the Bayesian calculation says, okay, calculate the profile likelihood, evaluate the likelihood function along this line. Everywhere, weight it by the width in this direction, but for this Gaussian example, that width is a constant, so you can just report the profile likelihood. But there are cases where the profile likelihood and the marginal likelihood function will look different. I just drew you some geometric examples here. So here's another joint likelihood function for a signal in a background parameter, for example. And imagine it was a flared distribution like this. Okay, so here's the best fit b parameter as a function of s. It's just it's a constant in this direction. But in this example, the background uncertainty is much bigger here than here. So here's the profile likelihood. Here's the value of this likelihood function along this line. That's this green curve here. But then the marginal likelihood function weights this by the background uncertainty, the width in the b dimension, and that gives you the blue curve. And so the Bayesian result is different than this profile likelihood result. So if you ever use numerical recipes, I think chapter 14 or 15, where they tell you to kind of minimize chi-squared as a function of the nuisance parameters, that's this green curve. That's profile likelihood in chi-squared language. And what Bayesian inference tells you to do is to weight that by something that that's proportional to the uncertainty in the direction you've minimized over. Here's another example. This kind of banana-shaped contour happens a lot in astrophysical modeling. Often there's some kind of underlying power law relationship that gives rise to correlations that look like this. So here, the best fit B parameter as a function of S would be this blue curve here. So remember, that means that it's right where the contours become vertical. That's what determines where all these blue curves are, even in the previous plot. It's right where the contours become vertical. That's the best fit value. That's where B, the likelihood is maximized in the B dimension. So the profile likelihood is evaluating the joint likelihood along that curve. That's this green one here. But because of the banana shape here, the B uncertainty is much bigger here than here, so that shifts the inference to those values of S. Shifts it away from the maximum likelihood value of S to values where there's more volume. That's what marginalization is doing. So marginalization, integrating over some part of the parameter space, comes up over and over again in Bayesian inference. We'll take a break after this slide. But I just want to point out all the places that arises. These are all uses of the law of total probability. So I just told you that you do this kind of integral to eliminate nuisance parameters. This is the calculation we just did. You also do this kind of integral to propagate uncertainty. So suppose the model has parameters theta, but we're interested in some function of theta, f of theta. What can I say about big F, the value of f of theta? Well, I want to calculate a posterior probability distribution for that. How do I do that? Well, the law of total probabilities says, well, I can insert something that will give me probabilities I know. In that case, imagine inserting the actual value of the model parameters. Expand. So the law of total probability says this equals this. Just sum over this slot. Now expand this with the product rule. This is P of theta given D and M, and then P of F given theta. This thing here is just the posterior density, which we know how to calculate from Bayes' theorem. I just copied it down here. What is this? Well, what's the probability that, of getting a certain value of F if I know theta? Well, I have a function that tells me the value of F if I know theta. So this is a delta function. This is a probability density that's a delta function in F. So I can propagate my uncertainty in the parameters to an uncertainty in any function of those parameters by doing this kind of integral. That's a completely general version of propagation of errors. The usual laws of propagation of errors that we learn, where you take derivatives and you know, square everything and sum squares and things like that. That's an approximate treatment that's only valid when there's lots of data and things look Gaussian. This is a treatment that, and models are linear. This is a treatment that's valid for arbitrary complexity, strongly nonlinear models, small sample sizes. So it's a very powerful thing to know, and it's a consequence of the law of total probability. Predicting future data. So what's the probability of seeing some future data d prime given the observed data? Well, I insert the parameters and integrate over them, law of total probability, and then I just factor this, and I can get this in terms of the posterior density, and then a predictive probability for future data. And that thing's usually simple. Like if there's additive Gaussian noise, this is just something like, you know, a Gaussian for each of the future data. So I'm doing like a Gaussian convolution against my posterior distribution. So the point of this slide is just to show that marginalization, integrating over parameter space, happens over and over again. It's why I like to say that the important theorem in Bayesian inference is the law of total probability. Bayes' theorem is important because it gives you this thing you need to do all these other things via the law of total probability. The final place it appears that we'll talk about is in model comparison, and we'll pick that up after the coffee break.